Hello everyone. In this video, you will learn how to find the average velocity and instantaneous velocity of a moving object, average rate of change and instantaneous rate of change of a function, their geometrical representation, and equation of tangent lines to curve. Now let's begin with finding the average velocity and instantaneous velocity of a moving object. Now let's think of an object moving in a straight direction. The first thing we would like to know about the object is the average velocity on a given time interval. The average velocity is defined by the change in position divided by time elapsed. In order to find the formula to compute the average velocity of a moving object, let's give the functional notation for the position of the object. So let's consider s equals f of t be the position function of the object at any time t. So that means if this is an initial position of the object at any time t, so s equals f of t denote the distance of the object from the initial position. To find the average velocity over the time interval t0, t1, so here f of t0 be the position of the f of t0 is the position of the object at time t equals t0. So let's say t equals t0. So that's gonna be f of t0. That's the distance of the object from the initial position. And when time t equals t1, so this f of t1 is the distance of the object from the initial position. So that the change in position over the time interval t0, t1 is given by f of t1 minus f of t0. So that's going to be this is the change in position. So that the average velocity or the average speed is given by the formula f of t1 minus f of t0 divided by t1 minus t0. It's denoted by delta s over delta t because it's the average velocity, and that's the change in position divided by the change in time. Okay, so now let's compute the average velocity of a falling object in the following example. So here Galileo discovered that the equation of motion of a falling object is given by the function f of t equals 16t square, where f is measure in feet and t in second. Find the average velocity of the object over the time intervals. Okay, so given time intervals. So here, so let's say this is the initial position and the object is falling down. Okay, so at any time t, so the distance of the object from the initial position is given by 16t square. Okay, all right, so then now let's compute the average velocity over different time intervals. So number one, on the time interval 1, 2, the average velocity is given by delta s over delta t, which is the change in position, which is f of 2 minus f of 1 over 2 minus 1, and that's going to be, you plug in t equals 2 and t equals 1 in the given function. When you plug in t equals 2 in the given function, you get 16 times 2 square minus 16 times 1 square divided by 2 minus 1. So you factor out 16, you have 2 square minus 1 square, that's going to be 3 over 1, and that is 48 feet per second. Okay, so that's the average velocity over the time interval 1, 2. So please make sure that you find the change in position and you divide that quantity by the change in time. Okay, it's a simple formula to compute. All right, so also find the average velocity over the time interval 1, 1.5, exactly the same way. So delta s over delta t which is gonna be f of 1.5 minus f of 1 over 1.5 minus 1. That's gonna be 16 times 1.5 square minus 16 times 1 square over 1.5 minus 1. So if you use your calculator and compute this, you should be able to get the number 40 feet per second. Okay, so that's going to be the average velocity over the time interval 1, 1.5. And on the interval 1, 1.1, the average velocity is again change in position. So f of 1.1 minus f of 1 over 1.1 minus 1, and that's going to be using the same function, 16 times 1.1 square minus 16 times 1 square divided by 1.1 minus 1. And if you use your calculator, so you will get the number 33.6 feet per second. Okay, again on the interval 1, 1.01, the average velocity, again change in position, that's going to be f of 1.01 minus f of 1 over 1.01 minus 1. That's going to be 16 times 1.01 square minus 16 times 1 square divided by 0.01. Okay, so here, so 1.01 minus 1 is 0.01, and if you use your calculator, you will get the this number to be 32.16 feet per second. Okay, and on the interval 1, 1.001, the average velocity is given by f of 1.001 minus f of 1, that's the change in position, and change in time is 1.001 minus 1, and that's going to be 16 times 1.001 square minus 16 times 1 square divided by 0.001, and that equals 32.016 feet per second. Okay, all right, so in this example we know how to find the average velocity just by using the simple formula, change in position divided by change in time. But I also want you to observe the fact that the time interval is getting shorter and shorter, and the time is getting closer and closer to 1. And if the time is getting closer and closer to 1, the average velocity is getting closer and closer to 32. Okay, if the time is very, very, very close to 1, so then the average velocity is going to be very, very close to 32. So that means 32 is gonna be the instantaneous velocity of the moving object when time t equals 1 second. Okay, so therefore the instantaneous velocity is at time t equals 1 second is 32 feet per second. So here the time is getting close and closer to 1. Okay, so in that case the average velocity is getting closer and closer to 32, so that's going to be the instantaneous velocity of the falling objects. So the instantaneous velocity is actually obtained from the average velocity by having the the time close to the given time. Okay, all right, so here, so we can develop a formula for the instantaneous velocity. So the instantaneous velocity at time t naught is actually, you approximate the time close to, or you you make the time close to t0, and that's the change in position divided by the change in time. So that's the average velocity. So the instantaneous velocity is obtained from the average velocity by making the time very, very close to the given time t0. Okay. All right. So that's the instantaneous velocity formula. We will discuss about this notation, limit notation, in the next section, but please understand that the instantaneous velocity is obtained from the average velocity by taking the time close to the given time. Okay. All right, so now let's generalize this idea for the average velocity, generalize the idea of average velocity and its instantaneous velocity for any function. Okay. So suppose y equals f of x is an arbitrary function, then the average rate of change, so here is going to be the average rate of change over the interval x0, x1 is given by the change in value of the function divided by the change in x values. Okay, so that's going to be the average rate of change, and the instantaneous rate of change is obtained from the average rate of change by making the x value close to the given given value of x, which is x0 here. All right, so now let's try to visualize this in the picture, or before that, let's work on an example. So find the average rate of change of the function over the interval 0, 2. So the average rate of change is given by delta y over delta x. Delta y is the change in function values. Delta x is the change in x value. So that's gonna be f of 2 minus f of 0 over 2 minus 0, and that is obtained by plugging these values in the given function. So it is 2 plus cosine pi times 2 minus 2 plus cosine pi times 0, okay, over 2. And 2 plus cosine 2 pi is 1, minus 2 plus cosine 0 is also 1, divided by 2. 3 minus 3 divided by 2 is 0. Okay, so that's the average rate of change of the function. All right, now let's try to visualize the average rate of change and the instantaneous rate of change of a function in graph. Okay. All right, so let's consider an arbitrary function y equals f of x, and this is the graph of such function. And let's assume that this is x0, okay, and we have x1, that's another value of x. The value of x is changing from x0 to x1. Then the average rate of change so the average rate of change of the function f of x over the interval x0, x1 is equal to, so that's going to be, that's a delta y over delta x, that's the notation, and that's f of x1 minus f of x0 divided by x1 minus x0. Okay. Right. So if you want to see this in the picture, so here x0, so this is the value of the function at x0, so that's f of x0, and this is the value of the function at x1, so f of x1, and f of x1 minus f of x0, so that's going to be this quantity here. So this part is f of x1 minus f of x0, and x1 minus x0 is this one, and which is same as this one, so that's going to be x1 minus x0. Okay, so here f of x1 minus f of x0 over x1 minus x0, that's going to be rise over run for this secant line. Okay. All right, in other words, if you represent this point by the coordinates, so p of x0 comma f of x0, and this point q, let's say x1 comma f of x1, then f of x1 minus f of x0 over 1 minus x naught is the slope of the secant line. So this quantity is the slope of secant line PQ. Okay, all right, so the average rate of change of the function over the interval x0, x1 is actually the slope of secant line joining these 2 points PQ. So now the instantaneous rate of change. So instantaneous rate of change of the function f of x at the value x equals x0. Okay, so this instantaneous rate of change is obtained from the average rate of change. So that's going to be f of x1 minus f of x0 over x1 minus x0 by making x1 very close to x0. So the notation for that is, limit x1 approach to x0. Okay, so if you make the value of x1 very close to x0, then you get the instantaneous rate of change from the average rate of change. And now if you would like to see this in the graph, so x1 is getting closer and closer to x1 is getting closer and closer to x0. In that case, the point Q will move towards P when x1 get closer and closer to x0. And when Q is very close to P, so this secant line will become a tangent line at P. Okay, so when the x1 is approaching to x0, the secant line will become a tangent line at P, and the slope of the secant line will become a slope of the tangent line. So that means the instantaneous rate of change of the function at x equals x0 is the slope of tangent line at the point P x0 comma f of x0. Okay, so the slope of the tangent line is actually given by this expression, which is the limit x1 approach to x0 f of x1 minus f of x0 over x1 minus x0. Okay, all right, so now let me write slightly differently for the slope of tangent line. Slope of So now let me write the slope of tangent line slightly differently. So slope of the tangent line at P is gonna be, sorry about that. So the slope of the secant line is f of x1 minus f of x0 over x1 minus x0. So the slope of the tangent line at P is slightly so the slope of the tangent line at P is given by limit, I'm writing x instead of x1, so x approach to x0, so the x value is getting close to x0, so f of x minus f of x0 divided by x minus x0. So x can be any arbitrary value of x that is being close to x0. So that's the formula for finding the slope of tangent line. So then using this formula we find the slope, and then we can write the equation of tangent line. Okay, so now let's work on an example to find the equation of tangent line in the next slide. Okay, all right, so equation of tangent line. Find an equation of the tangent line to the curve y equals x squared at the point 2, 4. So here so the point is given, so the point is 2, 4, and we need to know how to write the equation of a line. So for that we need the point and the slope. So the point is given, but the slope is obtained by using the previous the formula from the previous slide. Okay, the slope is slope of tangent line is given by the formula. So m equals it's the limit x approaches to x naught, so f of x minus f of x naught over x minus x naught. So that's the formula I just mentioned. So here the point is 2 comma 4, so 2 is x naught, so at the point, so this is the equation of tangent line at the point P x naught comma f of x naught. So here the point is given at the point x naught, which is 2 in this example. So the slope is given by so f of x minus f of 2 divided by x minus 2. Okay, all right, so now let's use the given function, which is x squared minus 4 over x minus 2. Okay, so now we need to find the value of this quantity as x get closer and closer to 2. Okay, so we need to find the value of this expression for x values close to 2. Okay, so for that let's make a table. So let's give the x value close to 2 which are less than 2. Okay, so here is x squared minus 4 over x minus 2. So the value of x that is less than 2, let's say 1.9. When you plug in 1.9 in this expression, you will get 3.9. And you plug in x equals 1.99, you will get 3.99. If you plug in x equals 1.999, you will get 3.999. Also, you can put the x values bigger than 2 but close to 2. So let's say 2.1. So the value of x squared minus 4 over x minus 2 is going to be, when you plug in 2.1, it's going to be 4.1. If you plug in x equals 2.01, the value of x squared minus 4 over x minus 2 will be 4.01. If you plug in 2.001, the value will be 4.001. Okay, if you look at these two tables, as x get closer and closer to 2 from the values of x that are less than 2, it's getting closer and closer to 4. If your x value is getting closer to 2 from the values of x that are bigger than 2, your value of x squared minus 4 over x minus 2 is getting closer and closer to 4. So that means the value of x approaches to 2, x squared minus 4 over x minus 2 is going to be 4. Okay, and that's the slope of the tangent line for the graph of the function y equals x squared at the point 2 comma 4. So now we have the slope and the point is given. So slope is 4 and the point is the point is 2 comma 4. So we can now write the equation of tangent line using the point slope form. So using point slope form, so the equation of tangent line at the point 2 comma 4 is y minus y1 is 4 equals m is 4 times x minus x1 is 2. Now if you simplify this just by adding 4 on both sides and subtracting y, you will get y equals 4x. It's minus 8 plus 4 is going to be negative 4. Okay, so that's the equation of the tangent line. All right, so please understand this. The slope is obtained from the this process. So you will have to work on several examples on the homework assignment, and we will also practice other example in the class. Okay, see you in the class. Thank you.